Can you check your notes and see, did we do number 74? Word is having, okay, I guess we did number 74. It just popped up here. I'm not getting my toolbar up here right now. I'm having, I think, a memory problem here. Let me see what I can get rid of here. Let's close this. Okay, so we did the determination of the molecular formula. That's pretty much the last part of this chapter here. And so let's take a look at the next chapter. It should be chapter 8. Chapter 8 deals with chemical reactions. Actually, chapter 8 and 9 both deal. There are more chapters. There's some chapters near the end, particularly with acids, bases, and redox that deal with chemical reactions. And so I'll be introducing some of those topics from the latter chapters a little early here. We'll probably take a look at those chapters as well. So chemical reactions is just dealing with the chemical properties. So let's take a look at this. When we look at chemical properties, there are different ways that we can organize and classify the chemical reactions. And so your book has a way of doing it, and then there are other ways too. But your book has divided into like 7+ different categories of chemical reactions. But the way it's organized, there's some overlap and there's some, there's some confusing reactions where they classify 2 totally different types of reactions as the same because of the pattern that they have. And so your book primarily looks for patterns, chemical reactivity. The patterns are just simple patterns, like, for example, combination of elements. If you take element A and you combine it with element B, then that would be classified as combination reaction. But they also classify combinations of compounds as combination reactions as well. And so you could take some compound AB and some other compound CD and end up with some sort of combination. So we're going to divide it a little bit differently. We're going to divide it into 3 categories of chemical reactions. So what are those 3 categories of the chemical reactions? And so 3 basic types. Chemical reactions. This is in no particular order, but we have one that's called metathesis. Metathesis just deals with ion combinations, what ions like each other. Actually, let me erase something here. So there are particular ions that like to combine and form more stable things. So we'll be looking at those. As a subcategory of metathesis, there's a very common type of metathesis that follows a very simple pattern. And this is called double replacement. It's a double replacement pattern. But this is only one specific type of metathesis. I mean, metathesis, you don't have to fit this double replacement type pattern. It could be others, etc. And so we'll be looking at the overall ion combination type reactions here. The second type of reaction that we'll look at are acid-base reactions. Acid-base, there are three types. The Arrhenius. This is just different ways of visualizing. The Lewis acid-base, or actually Bronsted. So let me insert that in here. Sorry, Bronsted, and then the Lewis. The Lewis are the most comprehensive way of defining. In fact, we could define all acid-base reactions as Lewis, all fit this category here, but Bronsted is a subset. And the Bronsted ones are easier to deal with, easier to recognize. The Arrhenius are an extremely small subset, and therefore it's not very useful. Extremely small subset. And so this is the universe of acid-base. The universe of acid-base reactions would be Lewis, but you don't want to look at the entire universe. Sometimes you just want to look at a specific galaxy of reactions rather than the entire universe. So that would be like Bronsted. Bronsted doesn't cover the entire universe. Instead, it looks at a subset. But when you do that, it makes things a little easier to predict and understand. And then Arrhenius is like looking at a single planet. It's not really going to tell you much about the whole universe of reactions out there. So we'd like to use Lewis, but Lewis sometimes is a bit more complicated. And so Bronsted pretty easy, or, relative to Lewis, it's pretty easy. Therefore, we're going to spend most of our time looking at Bronsted. Then three, the last type is what we call oxidation, reduction, or redox for short. Redox reactions. These they're a bunch of subcategories for this as well that we can look at. One of the big ones in your book is single replacement. And then we have redox combination. We have both. We have acid-base combination and redox combination. Your book doesn't differentiate between the two. Here. We could have combination over here as well. And so this leads to some confusion, possibly. And single replacement. Etc. So we're going to try to understand this. We're going to try to understand this a little bit better. Properties as related to composition and structure. So we know the composition. The composition is just the chemical formula, basically. Chemical formula. And the more detailed the formula is, the better. So for example, if we have an empirical formula versus a molecular formula, from the molecular formula, we can get some insight into the structure of that. From the empirical formula, it could just be a fraction of the of the structure. And so structural information is important in that sense. And in that sense, we'd like to know things like the molecular formula over the empirical formula. But not everything forms molecules, you know. Sometimes we form lattices and other stuff. So we'll try to get some structural information from the composition, from the formula. And from these, both of these, we'll try to understand the properties, you know. And so we're going to just focus on the chemical properties, but there are physical properties as well that we can try to understand, like melting point, boiling point, those types of things, you know, when we look at the structure and what's holding it together in more detail. Well, this I was going to write. So this is redox reactions. I broke it down into these categories: element plus element combination, decomposition, single replacement, chart redox method, or chart method, skeleton, etc. Redox, so single replacement, pros and cons, oxidation states. This is the chart that we use for the chart method. This is the steps in using the chart method here. Skeleton redox I'll talk about. Boy, that was short. So this is for redox. Let's take a look. I'll just give you a little preview. Actually, let me cancel out of this. See if this is, oh, okay, this is back. Took a little time to come back, but my notes are still missing. Anyway, I got this new computer, it has 16 gigabytes of RAM, but I just bought another 32 gigabytes. It's coming. But still, I'm thinking something's weird with this. Like I might have it like restricted how much RAM is being allocated to Word. Because 16 gigabytes should be plenty. But I'm gonna have 48 gigabytes pretty soon. Okay, so we're doing chapters. Okay, now it's not. It's odd. I thought the new computer would fix my issues, but it still has not. Well, PowerPoint's working, so we'll just do PowerPoint. Okay, let's see what else I have here. Oh, all right. This is why. So the three types of chemical reactions, talked about that. Then we have the redox, element plus element. So we got here. This is not, sorry, but I'm missing, seem to be missing two PowerPoints here. Let's see what happened. I guess I didn't copy them over into my new computer. That's all right. Just do it by hand. I'm going to see if I can open a new Word document, and maybe that'll take care of this issue. Okay. My new Word document. Something went wrong. So that shut down. One more time here. I can't believe this. I may have to reboot this computer. Let me see. Okay, finally got this back up. All right, let's try this again. Plus others. The others are acid, base, and redox. There's a chapter on that. Plus, there's a chapter specifically on redox as well. These are near the end of the book. I wish they. I'd like to cover these earlier, but it's all right. So we'll be covering some of this. Okay. So let's take a look at the three types of reactions. So let's do one. We're going to look at redox reactions first. And so I'll cover those here. The first type of redox reaction that we'll look at is going to be the element plus element combination. Now, what redox reactions are, these are electron transfer reactions. And so if we look at the periodic table here, the elements on the left, are metals. These tend to lose electrons. The elements on the right here, the nonmetals, these tend to gain electrons. And so we can kind of figure it out based on this. Yeah. So let's look at some examples here. The further to the right, the more it wants electrons, except for the noble gases do not want any electrons here. So let me block off the noble gases. Yes. Okay, so example would be sodium metal plus chlorine gas. Sodium is in group 1. So what will happen with sodium is that we'll form the ion. When we form the ion, we go from sodium to sodium plus. Okay, and we lose that electron, but the electron doesn't disappear, it goes somewhere. So where did this electron go? Well, the electron is going to go to chlorine. So if we have a chlorine atom, and that takes an electron, that's going to form chloride, like this. These are called half reactions, in a sense. So what's happening with sodium is it's losing electrons. What's happening with chlorine is gaining electrons. So what we're going to have is electron transfer. The electron is going to be transferred from sodium to chlorine, and that's redox here. And so in this case, I have 2 chlorines. Well, if I have 2 chlorines, each chlorine wants their own electron. And so if each chlorine wants their own electron, then I have to have 2 sodiums because 1 sodium is not enough. And so what I'm going to do is I'm going to double this. So I'm going to go 2 sodiums are going to form 2 sodium ions plus 2 electrons. Okay, and now I can have the 2 chlorines gain it. And so what I'm going to do is I'm going to do it like this. I'm going to put this as Cl2. And then I'll put this, because the 2 chlorines are actually bonded to one another. Sorry if this is getting too compressed here. But we'll do it like that just to balance things out. And so what we end up with is we end up with the sodium and the chloride, those come together to form what we call a lattice, an ionic lattice. And so we'll have 2 sodium chloride formula units that form on this. And so this would be an example of an element plus element combination. One element loses, the other element gains in this type. And so what element loses, the one's farther to the left. What element gains, the one's farther to the right gain. And so, yeah. Now, both of them might be kind of close to one another. So for example, carbon, we'll take carbon solid like charcoal. Charcoal, and react it with oxygen here. So if I take carbon solid, react that with oxygen, what's going to happen here is this. What we know is that carbon can lose up to how many electrons? Because in this case, carbon's further to the left, oxygen's further to the right. And so oxygen is going to be taking the electrons, carbon's going to be losing electrons. And so, let's see. Actually, four. If it lost all 6 of its electrons, that would be tough to do in this case. But it could lose up to 4. Even losing 4 electrons, might be tough to do. And so it might lose fewer than. So for example, here it might lose. It might just lose 2 electrons. That is, it might go to carbon and something like this, carbon and oxygen, carbon monoxide gas. That's possible here. So if we do this, then we need to balance this in this case. But how do I know that this is losing 2? Well, it appears to be losing 2 because oxygen is usually a -2. This is a -2. I'm going to put this in parentheses. And therefore, if oxygen's -2, that means carbon's got to be +2 in order to balance out the charge here. So we have +2 and a -2. Now, there's no charge here. And since there's no charge here, this is 0. And then these 2 oxygens, you might think, okay, that's a -2, but I have 2 of them. If you have 2 of them at -2, that would give us 2 times -2, which would be a -4. Well, that's clearly wrong because this whole thing doesn't carry a charge of -4. That means we have 2 of them at 0 charge, which gives us a total charge of 0. And so this is correct here. This would be incorrect. So in this case, when oxygen is in a compound, we'd like to give it a -2. But when oxygen is alone or bonded to itself in O2, then we don't give it a charge. This is what we call the element. And it turns out that elements are all 0 because they have no charge. It's the apparent ions. But these aren't your typical, ions like that we have. I mean, this is just more of a bookkeeping method. And it's a very useful bookkeeping method for understanding redox properties. So this is the oxidation states. The oxidation states are the apparent charge. They don't have to be the actual charge. Because, that +2 needs to be stabilized, and +4 needs to be stabilized here. But in this case, what we say is we partially oxidize the carbon. We'll talk more about what I mean by oxidize and reduce here. Now, there are 2 ways of balancing this. One way of making sure, I have too many oxygens here, right here, because I got 2 oxygens. So what I could do is I could multiply this by 1/2. Okay, it's not that I necessarily have half an oxygen molecule. What this could mean is I have a mole, because the atom and molecular ratio is the same as the mole ratio, is the same as the dozen ratio. So the way I can read this equation is 1 carbon atom, reacts with half an O2 molecule. Well, that doesn't make sense because we don't have a half an O2 molecule to give us 1 CO molecule. So since it doesn't really make sense, what I'll do is I'll double it. And so we'll just multiply this one by 2. And so we get 2 carbons. 2 atoms of carbon reacts with 1 molecule of O2 gas to produce 1 molecule of carbon monoxide gas. That's what we have here. And so in this case, that would work. This one would work if we're talking about moles, because moles is a huge number. Avogadro's number is worth. So if I had 1 mole of carbon, that would be 6.022 times 10 to the 23rd carbon atoms. If I had a half a mole, that would be 3.011 times 10 to the 23rd oxygen molecules. And this is going to lead to 1 mole of carbon monoxide. And so the ratios here are the mole ratios or the atom molecule ratios, depending if we're talking about particulate. If we're talking about particulate level, then we need to use this one. If we're talking about moles, then this is fine. We could have fractions of moles. It's not a problem. Having fractions of molecules, that would be a problem at the particulate level. So this is forming carbon monoxide. However, we could also go all the way to carbon dioxide. So there are multiple products for this because carbon can have variable charge. Whenever we have some species that can have variable charge, we have variable products. And so here in this case, let's go ahead and use the full O2, and then we can carry this all the way to CO2. Now, what is the oxidation state of carbon in CO2? The oxidation state of carbon in CO2, now this O2 is not this O2. When I look at this O2, I have 2 oxygens, and we'll look at these structures more detail later. It's like this. But when I look at this O2 is not a molecule of this O2 attached to a carbon. The carbon actually splits the 2 oxygens here. And so we end up with a structure that looks like this. This is CO2 here. These two lines represent what we call a double bond. You know, if I have a single line, it'd be a single bond, and 3 lines would represent a triple bond. Double bonds are stronger than single bonds for the same elements, and triple bonds are even stronger. Triple bonds are some of the strongest bonds you can have. Okay, these aren't ions. This is not an ionic lattice. And so when I say apparent charge, it's an apparent charge because unlike this one up here, this is an ionic lattice here. And the charges aren't apparent. These are actual charges. So when I look at the sodium chloride, the sodium has a positive charge, actually. And that's held together to the chloride by electrical attractions. We call these electrical attractions Coulombic attractions. So there's positive and negative attraction. That's what holds these together. But if you're a positive ball, what you want is you want to surround yourself by as many negative balls as possible. So how many negative balls can go around this one positive ball? Well, you know, in sodium chloride, we could put 4 negative ones in the plane, and then 1 on top here, and then 1 coming up from underneath. So if you're positive, you want to surround yourself with as much negative as possible. And in this case, the coordination is 6. That is, we can fit 6 chlorides around each sodium. Now, if you're negative, then you want as many positives around you as possible. And so we could fit 1 there, 1 here, 1 here. And that's 4 in the plane, and then 1 on top, 1 below. So that's also 6. So each sodium bonds directly to 6 chlorides, and each chloride bonds directly to 6 sodiums. And this lattice extends in 3 dimensions, etc., in 3 dimensions. Now, the structure of these is quite a bit different. These are not ions here. Even though I wrote, okay, +2, -2, this is a way of bookkeeping, of keeping track, because we started at 0. This is definitely 0, but it's lost some of its electron density. And so the bonding here is a bit different. These aren't formal ions per se. These are molecular structures. And molecular structures for carbon monoxide, it has a triple bond, which is quite strong. There's 2 dots there, 2 dots there. So it looks like this. It's not an ionic lattice like this. Instead, it forms molecules. And the charges here, we don't show the charges here. Whereas in an ionic lattice, we would show the charges, because the charges these are ions being held together. And so we'd have a sodium ion with a plus like this, and a chloride ion. Chloride ions are bigger, like that, with a minus, etc. This is one formula unit here. This is a formula unit. This formula unit is not a molecule. It's not equal to a molecule. And the reason it's not equal to a molecule is because it's not discrete. It's not an individual discrete unit like this, carbon monoxide here. When I look at the lattice here, which of these sodiums and which of the chlorides form a single discrete unit? And so, okay, so here we have this. Now in CO2, over here, if we assume, then this is what we're doing. We're assuming that oxygen is -2. You know, although as a ionic compound, you know, it would be -2, but this is molecular, but we treat it the same here. And the carbon, if this is -2, this is -2, this has got to be +4 to add up to 0, you know. This plus this is going to equal 0. Now, oxide can occur in ionic lattices. So for example, if we had MgO, magnesium oxide, solid, then we have magnesium 2+ ions like this, and then oxide 2- ions like this. And again, this would be a lattice. And so it extends in 3 dimensions. But we do have ions here, and so it's different. And so one way to recognize it, in ionic compounds, it's either ions that we have or metal and a non-metal. Metal and non-metals, typical ionic compound, whereas molecular compounds, typically all non-metals here. You can see these for molecular compounds in which we don't literally have the ions. And these are the ionic compounds over here in which we do literally have the ions. And so have ions here, don't have ions here, but treat, in order for bookkeeping, for redox reactions, we treat this. And technically it's not 100% accurate to treat it like this, but it makes, you know, it makes, if you treat everything the same, then it makes it easy to compare things, you know. And so we have everything like this, and then we start to make little comparisons with stuff. Now, how about CO3? Is CO3 a viable? Carbon solid plus O2 gas yields carbon trioxide gas. Is that viable? This is, yeah, I mean, it is possible, I guess, but, you know, like Cameron, you mentioned 6, this would be indeed losing 6. And if it did lose 6, then carbon has a total of 6 electrons. And it'd have to lose every single one of its electrons here. And so this would bring carbon in the +6, which means losing all electrons. Well, does it literally lose all? No, it doesn't literally lose, but in the context of this, it's essentially kind of the same thing, which means that this is like not very feasible as a stable product of this. Let's see if edge takes up this space. So if I do CO3, mostly it's going to be coming out as carbonate. You know, the carbonate is CO3 2-. Well, CO3 2- is not a problem because CO3 2- will have carbon in the +4. But what about carbon trioxide? You know, yeah, here, carbon trioxide. Let's take a look at this. Carbon trioxide. Carbon trioxide. Okay, carbon trioxide is an unstable oxide of carbon, an oxocarbon, possible isomers. Okay, we'll talk about that. Here they generated some structures of this. This has a peroxide link here. This is going to be very unstable. And these have what are called free radicals, which are very unstable. You know, these are would be fleeting. Like maybe you form this in the flame, but it's not going to last very long. You know, under the extreme environment of a flame, it might pop in there, but not as a stable product. And then the oxidation state is going to be is going to be normal. That is, what's weird that's happening is with the oxygens. It's not with the carbon, because the carbon is still going to be a +4 here. I'll show you another way of generating oxidation states once we get to these structures. These are called Lewis structures. But this carbon's normal at +4, +4, +4. These oxygens aren't your typical, like this would be a -1, -1, -1, -1. And so there's some stuff going on with that. Actually, these structures. There's not much written here about this, and I kind of wonder about the literature for this here. Carbonate's not a problem. There's tons of stuff about carbonate. So if we look at carbonate, CO3 2-. There's lots. Very common ion. Looks like this. Okay. So when we generate fixed charge, it's fairly simple. When we generate variable charge, we have variable products. So we know the carbon's variable charge. Variable charge equals variable products. That is the ions that we form. Fixed charge, we only have one product. Okay, let's take a look. Some more examples here. Next example would be something like iron plus oxygen. And so we look on the periodic table and see, what are the typical charges for iron? Oxygen, the typical charge is -2. It could potentially be a -1 as in peroxide, but peroxides are very unstable, so we try to avoid those. Let me grab a periodic table here so we can see. So when we look at iron, iron's in the +2, +3 region over here. And so +2, +3 is what we're going to have. And so if iron is +2, we'll just go like this. So iron at +2, and then oxygen is at -2, then what's the formula? The formula is just going to be FeO because the +2 and the -2 are balanced. And so that's, and then we call this iron 2 oxide, or this is the lower charge, or ferrous oxide. Ferrous indicating iron in the lower charge. The other alternative is we could have it +3. So iron plus O2 yields iron 3 oxide. And so doing iron 3 oxide, what is it going to look like? Let me just box this one here. Set that as default. Okay, getting the formula here, it looks like I'm going to need how many oxides? Well, there's a little trick you could do this. You could just keep adding them, or you could do this subscript trick. It's kind of like cross multiplying. So if we do the little subscript trick, then we get Fe2O3. That should balance it out. In other words, I need 2 irons, 3 plus, and 3 oxides, 2 minus. Let's try that over here. And so this gives me a total charge of +6 and total charge of -6. So it's balanced out here. And we call this iron, Roman numeral 3 oxide. So both of these are possible. We could form iron 2 oxide or iron 3 oxide, depending on how vigorous the conditions are. Now, balancing this one out, we could try a half. We could do a half here, or we could double the whole thing. And so we'll go ahead and double it. And so we're going to get 2 irons there and 2 FeOs there. Over here, I'm going to need 2 irons and 3 oxygens. If I need 2 irons and 3 oxygens, that's easy. I go 2 here, and then I go 3 halves here. Because this O2 consists of 2. So if I have 2 times 3 halves, that gives me 3. And so this works, but if I want to get rid of the fraction, then I'll double everything. So if I double everything, I'll get 4 irons solid plus 3 O2 gas yields. Double this 2 Fe2O3s. So then I check to make sure it's balanced. And the way I check is I have 4 irons. This 2 times 2 is 4 irons. 6 oxygens, 3 times 2 is 6. Then 2 times 3 is 6. And so this is what we say balanced. That is, all the atoms are accounted for in this. Let me save this. Okay. Now, for fixed charge, let's take a look at something with a fixed charge, zinc. Let's do zinc. What's the fixed charge on zinc? Yeah, +2. That's correct. Let's take a look at that. Okay, we'll just go. Zinc is in group 2B here. It's fixed. Zinc is fixed charge at +2. Cadmium is also fixed charge at +2, but mercury is not. Mercury is variable charge, +2 and +1. In group 1B here, only silver is fixed charge. So it forms this little elbow. Zinc, cadmium, and silver are all fixed charged. +1, +2, +2. The others are variable charge. Like copper. Copper, they're showing as fixed charge, but that's not correct. That's not correct because copper can be +1, +2. So this is just showing the most common charge. The most common charge of copper is +2 by far. Gold is variable charge too, +1, +3. And so let's go back to this one. So we know this is going to form +2. So who's it going to lose electrons to? So let's put phosphorus here. Now, what zinc wants to lose 2, and so we'll have Zn2+. But phosphorus wants to gain how many? If phosphorus were to gain, how many would phosphorus like? So you look at the periodic table and see. Currently, phosphorus is 15. And therefore, I'd like to gain how many to get up to 18? 3. That's good. That's correct. 3. And so phosphorus is going to be 3-. Now, there are 2 ways you could do it. You could just keep adding the ions up, or you could do this trick here. We'll do it again. And so we'll get Zn3, 3 zincs and 2 phosphides. This is zinc. Since zinc only has 1 charge, we don't need a Roman numeral. And this monatomics end with IDE. Zinc phosphide would be it. All right, why don't you try this one? Try aluminum plus oxygen. And tell me what you get. Aluminum plus oxygen. Pause the recording here. All right, did you guys get it? Anybody get it? All right, aluminum's fixed charge. Yeah, actually, switch that around. Aluminum is going to lose 3, not gain 3. So you would write Al3 plus. And then oxygen would gain 2. And so you'd have O2 minus. And then how many of each of these do we need? And so we could do this cross multiplying type deal and get Al2, O3. Since this is, yeah, that's correct. Since this is, actually, you're right. I didn't balance the last one. Aluminum, it's fixed charge, so we don't need Roman numeral, and we'll just call it aluminum oxide, like that. Here, I should balance this one. This one's easy to balance because it's just 3 zincs and 2 phosphoruses. This one's a little more tricky to balance because O is doubled here. And we have 2 here, but we have 3 here. And so this is the way I usually balance it. The way I usually balance it is I save the single elements for last, actually. I'll just save the oxygen for last here. And so we'll get 2 aluminums here. That gives me 2 aluminums here. And I have 3 oxygens over here. I need 3 oxygens, so I'll do 3 halves. So I do something like this, and then I'll double it. So I'll get 4 aluminums, solid, plus 3 O2 gas goes to 2 aluminum oxides. Yeah. That would be there. Now, it doesn't always have to be metal, you know, let's just do here. We're going to do phosphorus plus chlorine here. Now, in this example up here, phosphorus gained the electron because it was further to the right. Is phosphorus going to gain 3 electrons in this scenario here? What do you think? Yes or no? You know, we saw phosphorus likes to gain 3. Do you think phosphorus will gain 3 here? Yes or no, and why? Let's let me give you some more time here. Let's take a break right now. It's 10:45. So we'll take a break for 10 minutes and start up again after that. I'll pause the Zoom. The meeting controls here. Oh, there they are. All right, so can somebody tell me who will lose and who will gain when I mix these two together? Who's going to lose and who's going to gain? Okay, let's see what we have. Chlorine gains. All right. Chlorine has negative fixed charge. Chlorine can, actually chlorine can have positive too, you know, like in perchlorate, remember chlorine had +7 and chlorate +5, some of the others. And so it is possible that chlorine can lose, but what dictates that is who's farther to the right. And so in this particular combination, chlorine's further to the right. So chlorine will gain, phosphorus will lose. And so chlorine's going to gain, and chlorine likes to just gain 1. Now phosphorus can lose up to a max of what? Phosphorus can lose a max of yeah, don't forget to, you know, review your notes. And if stuff is confusing in the notes, ask me at the beginning of class. You know, we can go back and cover that. And so if this maximum positive charge stuff didn't make sense, make sure you get it cleared up, because I was just trying to help somebody recently for a quiz, but you know, they're trying to cram everything in one night. It's hard. And so just be aware to try to get that cleared up. +5 is correct. That's good. +5. But +5 is also, you know, losing a lot. Like, for example, here when we looked at carbon, you know, carbon can be +2 or +4. +4 is by far the preferred, like CO2, but carbon monoxide can certainly form. You know, there's nothing stopping it. Now, I gave you some patterns from the periodic table. And these things, like, you go, wow, that's just memorization or whatever. But, you know, these patterns are pretty helpful. And if you, it's easy to memorize if you just look at them regularly. You know, if you spend some time. Let's see, let me go here. And so these guys were the +2, +3, were the common ones. These guys are the +1. You know, this is +1, +2. This is +2, +1, +2. Actually, let's just do it once. You know, +1, +2. Obviously, these are rules. These aren't laws, you know, laws. These guys are +3. These ones here are +2, +4. You know, like carbon, +2, +4. If you look at silicon, silicon is just showing 4, +4, -4. Over here, germanium, +2, +4. Tin, +2, +4. Lead, +2, +4. These guys over here are +3, +5. You know, +3 in the lower, +5 in the upper. Nitrogen, +3, +5. Phosphorus, +3, +5. You're looking for these patterns, +3, +5. Antimony, +3. So phosphorus is +3, +5, and -3. Those are the common ones. And so here, if phosphorus is going to lose, it could lose +3. So I'm going to write this as a Roman numeral because this isn't going to form an ionic compound. So if phosphorus is 3, we'll put that down. And chloride is 1. We'll put it down there. We're going to form this. We're going to form PCl3. Now, this is what we call a molecular compound. Molecular compounds just consist of nonmetals here. And so we have a different naming rule for this. This is a binary molecular compound. So if you recall, this is called phosphorus trichloride. Or sometimes, now this is not according to our rules, but sometimes you'll see it like this. Phosphorus, Roman numeral 3, chloride. And so oftentimes it's helpful to know, you know, different names for like phosphorus trichloride or phosphorus 3 chloride, because you'll encounter those names. Let's go with being, let's see. So we go to Wikipedia. Phosphorus trichloride. It's you know, systematic name. IUPAC is International Union of Applied and Chemists, but also other names. Phosphorus 3 chloride. Phosphorus 3 chloride is much preferred over phosphorus chloride. Phosphorus chloride is very ambiguous. That's because there's another chloride of phosphorus that exists. What is it? So the other chloride is, when we have variable charge, we're going to have variable products. So the other variable product is going to be like this. It's going to be the phosphorus with the 5 and the chloride. Now, +5 is extremely high charge. So that's why I'm not going to write a +5. Here, I'm not going to write a +3. These are getting more and more difficult to strip the electrons off completely. And so anyway, let's bring that down here, bring that over there. And so we end up with PCl5. What's the name of this? What's 5? The prefix for 5. And so this would be phosphorus. Yeah, pentafluoride. Good. Pentafluoride. Now, fluoride has a weird, or chloride. Sorry, no. Chloride. Another binary molecular compound, and sometimes it's called this. Sometimes it's called phosphorus, Roman numeral 5, chloride. So let's take a look at this PCl5. PCl5. This is a different site. This is PubMed or PubChem. This is also a good site for information, here. Phosphorus pentachloride. This is from the National Library of Medicine, NIH. And the NIH stands for National Institute of Health. That's interesting. Interesting because I've been following, the ivermectin thing, and whatever you think of it, you can form your own opinions, which you should. You should form your own based on the data. But NIH was neutral on it, but the FDA and the CDC were against. So it's kind of interesting that they didn't come to the same conclusion. But anyway, going back to this, Okay, can you guys hear me?
Yes.
Okay. My computer just crashed, unfortunately, so I had to reboot it. Okay. Go back to, I got to bring up my documents again. It's weird. So I barely have anything on this computer. I only have my Chem 4 stuff. To see if there was some other issue causing this crashing. So see, okay. Okay, I didn't lose too much, I think. Here, unless this is 1039, 1055. Here. All right. And so one of the products with this was PCl3 here. The other one is going to be PCl5 here. This one was phosphorus pentachloride, as we saw. And then I was looking up online for PCl5. What was I looking for? Probably the alternate name. So reliable data. NIH is reliable data. NIH, government site.
Sir, I don't think you're sharing your screen.
Okay. So we're back to the NIH site here. I don't know what to think about the CDC site right now, but based on some of the information I've been seeing, but phosphorus 5 chloride here is an alternate name for this. And they give some data here, structures, etc. They have some 3D. It's failed to generate. All right, it didn't work. And then we can just balance this. And so balancing this one, I have 1 phosphorus and then I need 3 chlorine. So I use this, the fractions trick. So I'll get 3 halves. And then I can double it if I want. If I double it, I go 2 phosphorus plus 3 chlorines yields 2 PCl3s. And the same thing here, phosphorus plus chlorine. And then I want 5 chlorines here. I have 1 phosphorus, 1 phosphorus. And I need 5 chlorines here, so I'll just multiply by 5 halves. And so I could leave it like this with the fractions, or I can double everything to get 2 phosphorus plus 5 chlorines yields 2 PCl5. PCl3 is a gas. Phosphorus is a solid, chlorine's a gas. PCl5, I don't know if that's a gas or a solid, but we can easily find out, based on this. It's a solid. And so both of these are nasty. I used to work with PCl3 a lot, and it's very reactive. And so this one is a solid, this is a gas, this is a solid here. What else did I want to do? Now, there's some other ones that are a bit tricky here, like fluorine plus oxygen. Now this is kind of a odd pairing because, who's going to take the electrons, fluorine or oxygen? Yeah, fluorine. That's good. You spell it. Let me check if I'm recording this. Okay, it's still recording, oddly enough. So even though my computer crashed, it didn't stop recording. That's good. All right, so fluorine's going to gain. So fluorine's going to gain 1. Now the anions go second. So even though I wrote this first, it's not going to be positive. And then that means the oxygen has to lose. Well, how many does oxygen want to lose? Oxygen can lose up to 6, but that would be huge. Huge. And so in this case, we're just going to have oxygen maybe lose 2. We have 2. There's other ways of figuring this one out, because here we could have variable products like we had before. But one of the ways of figuring it out is like OF2 is like H2O, except we have fluorines instead of hydrogens here. And so it looks something like this. And so structurally, this helps us because if we know how oxygen, bonds like this, we can kind of figure out, well, it should bond to 2 fluorines. Oxygen likes to form 2 bonds, whether it's 2 single bonds like we have here or 1 double bond. Sometimes oxygen will form 3 bonds, which we'll talk about later. But we try to use, lots of information to help us understand this better. And so in this case, oxygen is going to be +2, here. It likes to be -2, but fluorine's going to win. So fluorine wants to be -1, -1. So that means oxygen's got to lose. What do we call this? We call this oxygen difluoride. Oxygen difluoride. Covered. Close enough. It's 10:16 now. I want to talk about the labs here. So this is a combination, element plus element combination. So I spent a lot of time talking about this, but there's some more we need to talk about in terms of redox. This one, I'm going to get rid of this one. Okay, here are my other notes. So this finally came back. I'll just start a new set of notes here. All right, unfortunately, it didn't work. It didn't save my document. Well, actually, I'm not going to bring it up. Let's talk about it here. Yeah, we're going to take a look at the hydrate lab tomorrow. But what about the other labs? You know, I need to start collecting. I haven't been on top of it for collecting the labs. And so I need you guys to turn in the labs. We can check those. And so it'd be good to get the labs tomorrow. Let's see. This is your device activation limit. You've reached your device activation limit. Desktop. Okay, now. All right, sorry. It's not letting me open this thing here without giving me too much trouble. Finally. Okay, tomorrow's lab. Experiment 4, the percent water in an unknown hydrate. So what can happen is we can have these ionic lattices. And do this. Okay. This came out backwards. Oh no, I got that. Second page. What happened to my first page? All right, wasting a lot of time here, but I think that's it. All right, so you're going to have some unknown. Oftentimes we're going to have these unknowns. Like we already had the unknown metal that you had to determine the density for. And so unknowns are a big part of chemical labs, and your grade sometimes can heavily rely on how well you do your unknown analysis. And so you'll have to record an unknown number. The unknown number you'll get from the stock room. It's either going to be on the sample. So make sure you write the number down. Now, what we want to do is we don't want to start marking this up because this is going to be your formal report, unless you make a copy of this, which is fine. You can make a copy and then put this into your lab notebook or something. That works too. Or you can copy it by hand, you know. But the formal report, you need to keep clean. You know, the formal report, which is going to be this sheet, it can be done in pencil. Pencil, okay. You don't need to do it in ink. But your raw data, you know, this is raw data here. You need a permanent record of your raw data. So let's say you wrote all your raw data here. So you mass of crucible and hydrate, et cetera, et cetera. And then you gave this as a report, a formal report to somebody. And let's say that somebody never returned it to you. Then what that means is your record of ever having done this experiment is now gone, you know, because you gave away your original data. And so that's something that's just not done. You never give away your original data. Otherwise, you have no record. And that means having to repeat stuff. And so what we need is we need a permanent record of the experiment. The permanent record of the experiment is your lab notebook. And so your lab notebook is where you want to keep your raw data here. And that's for your personal record. And this is not meant to be given away. You know, reports are meant to be given away. And so your lab notebook is should be in ink, you know, because pencil fades over time. And so it should be in ink. If you make a mistake, then let's say you made a mistake 1, 2, 3, you don't have to worry about neatness. You know, you can just cross it out here and then just correct it 0.13 grams, you know, the centigram balance, like that. And so don't use whiteout, no whiteout. Because sometimes the whiteout will flake off and expose the incorrect number. So you cross it out with a line like this. And don't do this. Let's say this was wrong, 0.123 grams. Don't scribble it out like this, because it should be legible what's underneath. And so this one, we don't want to do that. And so just a simple mistake, we can correct it like this. And so you can make a mess out of your lab notebook. It doesn't matter. You're not going to be graded on neatness, you know, here. But you don't want to make a mess out of your formal report sheets, because your formal report sheets are, you know, sent out to make it a positive impression. And so if these are a mess, then it sends out the wrong impression. All right, did I miss something? You know, oh yeah, I did 4, 5. And so let's take a look at the previous pages here. This is just the data. Let's look at the write-up for this experiment. Objectives. To determine the percent by mass of water in an unknown hydrated salt. So percent by mass of water, what do we need for that? Actually, let me just copy these. We did the last page, sorry. I can't select more than once. Okay, so what do we need for percent by mass of water? Okay, percent H2O by mass. Well, what we're going to need is we're going to need the mass of H2O over the total mass times 100%. They'll give it to us. And so we need the total mass of the sample. Well, that's something we can figure out. We just weigh it. And so you get a sample of the hydrate, weigh it, and that's going to be the total mass of the sample. Then you take that sample and figure out how many grams of H2O you have in that sample. So we got to figure out how we can figure out the number of grams of H2O contained in that hydrate, because the hydrate is going to be a lattice like this. It's going to be crystalline lattice. It's a salt. Salts are just ionic compounds. And what can happen in a lattice like this is we have, a whole bunch of ions that are packed together. The positive one is surrounded themselves with as many negatives as possible, and vice versa. And so what can happen is the waters can work their way inside the crystal lattice. There are gaps here. And so water molecules are quite small. And so they can fit into these little tiny spaces here as water molecules here. So we can get waters wedged in there. And so that's a hydrate. And this is, once it's been saturated, you've in other words, you put as much water as you can into the lattice itself. And so that forms a stable hydrate. Not all ionic salts, not all ionic compounds will form hydrates. Many of them don't want any waters in the lattice. But they can get water on the surface, though. Water molecules tend to stick to the surface of the crystal. It's different. Surface moisture is different than waters of hydration. To determine the number of water molecules per formula unit of the unknown hydrated salt. So is there 1, 2, for example, here, if we looked at copper sulfate likes to form a pentahydrate, or 5 waters. And these waters get into the lattice itself. So you got copper ions and sulfate ions in there. And so this is the mole ratio. For every 1 formula unit, we have 5 waters. So it's a 1 to 5 mole ratio. And so we're going to calculate that ratio here, number of water molecules for a formula unit, 5 to 1. Here's the copper. This is copper 2 sulfate pentahydrate. This is barium chloride dihydrate. And so it doesn't fit as many waters as copper can. Well, look at sodium carbonate. Sodium carbonate can fit up to 10 waters per formula unit. That's huge, decahydrate. And so there's got to be a lot of space for all those water molecules in that crystal lattice. The stability of hydrates varies. Some spontaneously lose water molecules, the efflorescent, and others must be heated to high temperature to give off. So this is some vocabulary here. Efflorescent, they spontaneously lose water molecules. Hygroscopic means they love water, and things like this will suck water out of the air. And so if you have humidity, you could dry out the humidity if you had lots of copper 2 sulfate. It'll make the air very dry because this will just keep taking the water. Some take up so much water they deliquesce. And so deliquesce is when they keep taking up water, and eventually what happens is it gets more and more water, and eventually it gets so much water that it forms a little pool and forms what we call a solution, not a hydrate, which is a solid. And so probably we could take a look at this visually to do efflorescent. Fluorescent. Yeah. I guess efflorescence is O, no OU. All right. So geology class of gym, efflorescent minerals. Let's take a look. Basement waterproofing, efflorescent. Efflorescent happens with plaster. Let's see if we have some efflorescent. Spell it. Efflorescent. Plaster. Let's see. On plaster walls. This is happening in like different places. So you get this kind of situation where the walls start to crack because the waters of hydration start to spontaneously come out, and then it causes this kind of damage. Okay, thanks. Wow. And this happens in like ancient, like I went to the Getty Museum, and they have a lot of research, and not only are they trying to protect you know, paintings and that kind of stuff, they're also trying to protect ancient architecture. And so let me see if the Getty, if they have any information on their efflorescent project, which I went to a presentation on at the Getty Museum. And they sent out teams of scientists out there to help preserve this architecture. Preservation, let's try that. And so they're trying to, like, there you get lots of efflorescent, and I think the ones that I saw were in Mexico. And they have these plaster buildings that are starting to blister and chip away, stuff like that. But it's pretty interesting. There's a lot of scientific research going on with the Getty right there off the 405. And so that was like the third or the fourth talk I've seen there. Then I've gotten, they'll give tours, you know, of the science labs there too. We went with the science club here at El Camino. I went there like 4 times. I'm sure they still go. Let's see what else we got here. That was efflorescent. And then we have hygroscopic. Hygroscopic is pretty interesting because you can visually see this happening. Let's see. No. Hygroscopic. Okay, here. Hygroscopic will just start to pick up water. And the deliquesce, they pick up so much water that it just turns into a pool of liquid. What is wrong with this? Oh, you could see it here. You know, this dried out copper 2 sulfate, which is white, is very
Professor, you're on mute.
all right. Today has not been very smooth as far as it goes. So I was saying that So you didn't hear anything I was saying earlier? Okay, hydroscopic materials will suck, water out of the air. So if they didn't put the dropper here, eventually this would turn blue by sucking the water out of the air. And then deliquescent, hydroscopic materials are used as desiccants. Desiccators just dry, they'll dry the air, desiccate the air, water. So they're used as desiccants. And so copper 2 sulfate anhydrous, the form without water, can be used as desiccant as well as calcium chloride. The copper 2 sulfate is expensive though, so it's not really common. But it's great because it indicates when this stuff gets wet, you can tell it's wet by the blue color. And then you have to dry it out again. Sodium hydroxide, like this, is what we call deliquescent. That is, it sucks water out of the air, and it sucks so much water out of the air, it forms a little pool. Let's see if we can see the pool of water form from this sodium hydroxide deliquescent. You can start to see little puddles there. Okay. That's fine. This is not the greatest. Here. So this is basically what we're going to do. Calcium chloride, sodium carbonate. We don't know which one we have. So what we're going to do is we're going to figure out which one we have. We're going to take hydrated salt and then heat it. We're going to heat it to drive off all the water. And so what we're going to do is we're going to weigh this before and weigh this after. And the difference will be water, how many grams of water. So the initial minus the final will be the grams of water that were driven off. Now we got to make sure we dry it. How do we know it's completely dry? Well, the way we're going to know that it's completely dry is we're going to heat it to constant mass. And so experimentally, a hydrate is heated to a constant mass. That is, the mass doesn't change. So we'll heat this and then weigh it, and then heat it again and weigh it. If the mass went down, then we still are driving off water. If the mass didn't change, then we've driven off all the water. So we're going to heat it to constant mass. How many heatings that takes just depends. And then that's it. That's all our data. So we just got to collect that data. And so here's the procedure. Obtain an unknown from the stock room. Now, when you get your unknown, how many trials are we doing? So we got to take a look at the number of trials. We're doing 2 trials. And so what you have to do is you don't use all your unknown on one trial. Then you'll have to make a second trip to the stock room, and the stock room is not going to be happy because you're making a second trip there, and you're not following the procedure as written. And so make sure you follow this carefully, because you might be only given one unknown sample that has to be divided into 2 for your 2 trials. Okay, let's see. So we're going to use a crucible. A crucible is this white porcelain thing that you tried to collect the soot. And so you'll have to clean the soot off your crucible if there's a bunch of soot on there. And it's just a dish. And so you'll put the hydrate in there and weigh. So you're going to weigh the crucible alone. And then you're going to weigh the crucible with your hydrate in there. Okay, so get that. Massive crucible and hydrate, massive empty crucible. This is reverse order. First, you got to weigh the empty crucible. Then you weigh the crucible and the hydrate. So this is reverse order data. The only reason they put it in reverse order is so we can easily do the subtraction. The larger number on top, the smaller number on the bottom here. Then this calculation is easy. Okay, so approximately 3 grams, but we need to know precisely, with as great of accuracy as possible, how many grams of hydrate we use in there. And so this is crucial. I don't know how many times people just, oh, it says approximately 3 grams. So how much did you put in? I put in 3 grams. Well, 3.00? No, just close to 3. you know, and so you have to be precise here. If you go under or over, it's no big deal, but whatever it is, mark down all the digits on the balance. Okay, and then we're going to put it on a clay triangle and heat it. Now, you got to heat it gently and slowly at first, because what's going to happen is, you know, when you have water, it's like popcorn. You know, you have water trapped in the popcorn kernel, and if you heat it rapidly, what happens is the water in there turns to steam quickly, and then it creates a lot of pressure. And the same thing can happen here. If you heat it rapidly, the water inside the crystal is going to turn into steam and break apart the crystal, and you're going to have little popcorn kernels flying out of your crucible. You don't want that. And so what you need to do is you need to heat it. You need to like try to drive the water out of popcorn without getting it to pop. And so the thing to do there is just drive it out slowly, you know, so you don't generate a big steam pocket. The same thing here. Be careful. You start off slow, and then, you know, once you got most of that water out of there, then you can heat it vigorously here. But you don't want to heat it too vigorously, because it'll liquefy. And so if your unknown liquefies, see note A. If it does not, see note B. So note A is for most unknowns that liquefy when heated, use low heat until they re-solidify, then gradually increase the heat and heat strongly for 10 minutes. Okay, we always got to watch out for splattering, you know, because splattering is going to ruin our experiment. That is, if some quantity gets splattered out of that, then there's no way of tracking that. Okay, B, if the unknown does not liquefy, gradually increase the heat and then heat strongly. Okay, so once we're sure we got most of the water out of there, then we can heat strongly for 10 minutes and then it should be good. Cool the crucible. We don't want to weigh a hot crucible, for sure. So we cool it on a ceramic plate and then weigh the crucible and its contents once it's cooled down. Okay, record the mass on the data sheet. Record the mass in your notebook would be best. Okay, heating the constant mass. To determine if all the water has been driven off, return the crucible with clay triangle and heat an additional 5 minutes. Cool and reweigh. If the two weighings do not agree within 0.04 grams, you must heat the crucible and its contents third time, 5 minutes. And so if we lose more than 0.04 grams, then heat it again. You know, ideally, it shouldn't lose anything. It should, you know, the two masses should agree. And so it's your call. You know, you could get it to do it or not do it. Yeah, pretty soon. Okay, use the mass. Okay, reproducibility of your results. Use another portion of your unknown and repeat all of the above steps. So this is trial 2. This is just a repeat. So this experiment doesn't take too long, except for the constant heating. So you gotta make sure you heat it. And then you have to eat it carefully. So, you know, first one you want to do slowly for sure. Okay, and then we have calculations for this that we can do. You know, calculations we can talk about later, or you can work on these. And then these are some errors, common errors that might happen in this experiment and how they might impact your results. You know? And so some solid material splattered out of the open crucible during heating. So if we lose some solid material, it's going to look like we have more water, you know, because the mass went down more than it should have. And so that leads to a higher error, that is a higher percent water. The hydrate was not heated at constant mass. That means that's less water, you know, because we didn't get all the water out. And there should have been more water, so that's less water. That's more water. It appears to be, etc. And so different things here. Okay, any questions on this? Now, when you set this up, you know, the best way to set this up, let me just go switch back to this. Is to mount the ring up high. And so you're going to have a ring here, and then you're going to put a clay triangle here. And then you're going to set the crucible inside the clay triangle, which is this white porcelain thing. It's just a bowl. And then you're going to heat this crucible. Now, when you heat this crucible, what you want to do is you want to hold the burner in your hand. That way you can control the heat. And so hold the base of the burner in your hand, in the palm of your hand. This is usually what people do. To better control the heat. That way you can move the flame along the different parts of the base of this. We're not going to use a wire gauze. We're going to heat this directly on there, but we're not going to heat it on the hard part of the flame, the hard part of the flame being the tip of the cone. We're going to heat it on the soft part first, all around, get it really warm and then hot. Okay, so that's why you're probably going to mount this higher than you normally would, you know, with a stationary burner. You put a stationary burner, you can't mount this too high, but in this case, you can mount it high. But be careful because you don't want these little popcorn chunks to hit you in the eye, you know. Actually, I guess you'd be this way, looking at this. And so be careful, you know, if something were to splatter out and hit you in the eye, that wouldn't be very good. And so make sure you have your goggles. But then again, you don't want anything to splatter out because that's going to ruin the experiment. So just be careful when you heat this up. Okay. Well, that's a lab. Now, were there any questions on the other labs, the report sheets? Okay, what I want to do is, since we have 5 minutes left, I'm going to continue with Redox. So we talked about element combination. We're going to talk about decomposition. Decomposition is the reverse. So for example, what would the name of this? Okay, can I explain primary versus minor species for experiment 5? Okay, experiment 5. Don't worry, experiment 5, hold off on that. You don't have to turn in experiment 5. Yeah. The reason is because for this electrolyte stuff, I got ahead of myself a little bit. I haven't really talked about it. And so I'm looking for experiments 1, 2, and 3. You know, experiment 1, though, it's just a burner. We didn't quite finish all of that. Go back to experiment 1. This glass blowing stuff is fun. Unfortunately, we don't do it anymore. All right, so these questions you should be able to answer. So number 8. Number 8. Don't do. All right, so then try this quiz. All of these you should be able to do. Even though this is for glass, you know, it shouldn't be too hard to answer that one. Now, when you do these, don't forget here, if it's false, like, let's figure out one. Number 2 is false. And so that being false, I need to draw a shape here. Let's see. So what we need to do is we need to check this and correct this. So here. And so the correction here is going to be this. It's not, the purpose is not for nitrogen. Come on. The purpose is for oxygen. Oxygen. And so false oxygen. Okay, my pen doesn't work very well with it. Adobe Acrobat. So work on 1, 2, and 3 and get those in as soon as possible. Okay, we're out. Sorry. Yeah, that's it for today. I'll see you guys in lab tomorrow. I'll stick around here. Liz, which worksheet? The one I have up here? That worksheet's in your lab manual. It's on the second half of the lab manual. So take a look there. Okay, let's see. The worksheet is the formal report. You know. Turn in. Yeah, no problem. All right. Yeah, thanks for you're here. I didn't quite get rolling, so appreciate it. I'll see you guys tomorrow. And if there are more questions, I'm sticking around, so go ahead and answer. Let me ask. Okay, thanks. You too.
Professor,
Yes.
I'm going to be missing 2 labs, the 12th and 19th, because I'm going to be out of state.
Which labs are those? Do you know the topic?
Let me check right now. The chemical reactions.
Okay. Yeah, that one unfortunately is probably going to be hard to make out. We'll see. So you might not be able to make that one out. But you probably can get some points from doing the reactions, the equations for the reactions.
Okay.
Yeah, thanks for letting me know that. Do you guys
You're welcome.
have any questions, Esmeralda or Mariah? Vanessa, send me a reminder though.
Like email you?
Yeah, when you're gone, when you leave, so then it's fresh. I'll probably forget by then, so that's why.
Okay, I'll do that. Thank you.
All right, thanks. Mariah, did you have any questions?